Okay, so now let's consider another configuration of current. So let's say we have an infinitely long cylinder. Again, infinity comes in because we want to create a situation of symmetry. And so we imagine that this is an infinitely long tube, and we take the infinitely long current-carrying wire and we wrap it around this tube. So if we make the drawing, here's the infinitely long current-carrying wire, and I can't make a very tight windings, otherwise I'll go on forever and it won't illustrate the idea, but we're going to wind this wire around the tube. I think this sort of captures that, and so on. Right, so this goes on indefinitely, and we can have current flowing one way or the other through the infinitely long wire that now is tightly wrapped around this tube or solenoid. Let's say that we have the tube or solenoid has radius r, and so if we look at it from the perspective where it's tightly wound, then we basically see a bunch of loops like that. It's like a bunch of little loops stacked on each other, and the density, the number of loops per unit length, is n. So, and there's current going through them. So we have current I or I naught, and we want to find the magnetic field. So we want the geometry and the magnitude of the magnetic field. So what we have is a situation of symmetry. We can recognize that if we want the magnetic field, say, out here, at that point, at any distance from the tube that's fixed, or from the axis of the tube, so this is the axis of the solenoid, and if we're at some fixed distance from there, right, if I move downwards or upwards, then the magnetic field there has to be everywhere the same, and that's also true of some other location. So, for example, if I move further away, now there's no expectation that the field should be the same here as it is there, but the field here, whatever its value is, must be the same everywhere along here, and whatever the field is here must be the same everywhere along there by symmetry, given how the current is distributed. So if we try to do Ampere's law there, what would we get? Well, let's say we call the length of this side L, and we call this W. So we want to recognize that the field has a certain kind of geometry, which we can get by considering the basic principle, which is that magnetic fields circle around the source. So if we take one little loop, now we can think of this entire current configuration around the solenoid as a bunch of little loops of current, and magnetic fields circle around, so each little loop will produce a magnetic field that roughly looks something like that. But if we add more of these little loops, right, we start to stack more and more on top of one another, and we still want to satisfy the principle that magnetic fields curl around the source, then we have to stretch the field out like that. And of course, as we increase this, we make many more little loops, and I go further and further, I'm going to stretch the field basically out into straight lines, right, as I go to infinity. And so out here the field is pointing either this way or that way, depending on the current. depending on the current direction, whether the current is flowing this way, or that way. So the field is either pointing this way or that way, and so when I integrate around, so let's think of applying Ampere's law to that path. Right, that's equal to mu naught I enclosed. So if I integrate with dl that way, then it looks something like this. Right, I'll draw a few dl's. Now I've chosen to integrate counterclockwise. Okay, if I do that, then what I'll get on this side is, well, let's assume the current is flowing such that the field is pointing, would be pointing upwards. Then I would just simply get the magnitude of the field. Let's call it B at this second distance, B2 times L. Then I come here, the field is pointing upwards. I get nothing because the dot product gives me 0, right? Magnetic field and dLs are 90 degrees from each other. Here instead, the magnetic field is pointing, so it would still be pointing this way, and so I get minus, but it's the magnetic field at 1 times the same length L, and here again I get nothing because the field would be pointing that way, and that's equal to mu naught times the current enclosed by this path, and there's no current going through there. So that gives us 0, and all that tells us that the magnetic field at this location, anywhere along here, must have the same magnitude as the magnetic field anywhere along there. But I could do this, I could push this loop out, or take this side and push this side out as far as I want, and the calculation would be exactly the same. Nothing would change. But I created this magnetic field from the infinitely long current-carrying wire, so I know that at an infinite distance away, the magnetic field is 0, because the magnetic field of the infinitely long current-carrying wire goes to 0 at an infinite distance that way. Right? So I know that if I take this side and push it out to infinity, I'll have the exact same calculation. But I also know that that B2, which goes out to infinity, must go to 0. And what this calculation tells me is that B1, the field close to the solenoid, must therefore be 0. So that means that the field outside the solenoid goes to 0 as I make the solenoid infinitely long. So there actually is no field out here, and we can sort of get a sense of this by recognizing is that the more I stack these to infinity, I'm making it harder and harder for the field to come back to itself. So eventually, the field comes back to itself at an infinite distance away, and so the field nearby, or anywhere actually, unless I get to infinity, is 0. So the field of a solenoid basically looks like straight. It's straight inside and 0 outside. So now we still don't have the magnitude of the field inside, so we want a path that goes through the inside. So let's consider a path that does something like this, and we might as well make it just as long with side L, and then we come out like that. What does Ampere's law say about that path? Well, so we're integrating on this path out here, or we get 0 because we know there's no magnetic field there. But when we integrate along this path, we have whatever the magnetic field is. It's everywhere the same in here because we are at some fixed distance from the axis of the solenoid, and every point sees the exact same current configuration. So we get the magnetic field. Let's call it somewhere inside the solenoid times that length, which is L. And no contributions anywhere else, because here and here, just like out here and here, the field is not pointing, it's pointing perpendicular to the dLs. But out here we know the field is 0. So the only thing we get from the left-hand side of this is this. And then In this case, the right-hand side is mu naught, but there is current going through this, going through the area that has this as a boundary. It's right here. We can see it right here. Right, so maybe another way of drawing this would be to consider this, and then we have current here that's either going in or out through this area. So another way to look at this, let's look at it from the top. So the solenoid, we see the disk, and the current is flowing this way or that way, and our little loop looks to us like that, and so we can see that current is going straight through it here. How much current? Well, it depends on how many loops there are, and so it's the density times the length times the current that's going through the wires. So and so what we get is that the magnetic field inside is mu naught n I naught. So I notice that it doesn't matter whether I move this a little bit closer to the walls or I move it towards the center. Right, that part doesn't come into the calculation because the magnetic field here is perpendicular to the DLs. And so that distance doesn't matter. So I have the magnitude of the field. Let's write this as B overall as mu naught n I naught. And if we want to do a coordinate system where this is the z direction, then we'll just put a k hat there. Okay, that's a general enough expression for the magnetic field of the infinite solenoid.